Okay. Practice makes perfect. Daniel, Ami, can you hear me? Can use the chat. Daniel, Ami, can you hear me? Yes. Okay, fantastic. Just prepare. We'll need this one, and we'll need. Okay. Plans for today. A few more geometric data structures. A bit more about painter algorithm and BSP. And then switching to modeling, getting to the very classical Hermit curves, B-spline, etc. Any questions? Okay. To remind you, BSP in general, any data structure that essentially tries to pick, you have a bunch of objects in 2D, 3D. For example, triangles, we pick a line in 2D or plane in 3D that hopefully does not cross too many of these objects, hopefully none of them, subdivide the objects into the one on the left, the one on the right, hopefully with equal numbers or close to equal numbers in both sides. And now we recurse on each one of the sides, creating now in the next levels. Well, these are lines or planes that are stored in individual nodes, and each such line or plane is relevant only to its own subtree. So we might as well think as this line as it's being cut once it hits a higher hierarchy of lines. Starting from the root, once a line from lower hierarchy meets a line from lower hierarchy meets a line of higher hierarchy, one of its ancestors, we'll just render it as stop because it's not relevant for anything else. And just to remind everybody, every node V is associated with R of V, which is the region of V. That was BSP in general. Quad tree was an example. If you allow me to think about the four children of a node, or the children of a node, as two children that has two children, and in octree tree that has two children, instead of a immediate node that has 8 children. But it was completely relevant. We talked about octrees, quad trees, when we stored a triangle possibly in multiple nodes, as opposed to points. We cannot guarantee for triangles that the triangle will be stayed only on one leaf. And then we need a stopping condition, for example, that once one of these quads intersect only a single triangle, then we don't feel any need to split it anymore. So a leaf will be either empty or contains or intersect at most one triangle. If a leaf like this node that was a leaf at some point intersect 1, 2, 3 triangles, that is R of V intersect more than one triangle, then we split R of V. Let's remind you the painter algorithm. Why am I teaching you about painter algorithm? Is this really the best way to remove hidden surfaces, to do the hidden surface removal in geometric scenes with a lot of triangles. Sometimes it is. Just to remind you what are hidden surface removal, I have the 3 triangles to render, and I want to have some decent order between them, so I'll render first the one that is furthest away, if possible, the one that is furthest away, then the one closer to you, then the one closer to you, and so on. And the idea is that if I render the green triangle, kind of triangle, and then on top of it, the red triangle is closer to you, then I don't care for each pixel, is this closer or further. It's just the moment that I decided to render all the red pixels, each and every pixel in the red rectangle is rendered red independent and ignored completely what was rendered earlier. That was a painter algorithm. Good application where you have an elegant such order, and that really saves a lot of work about what intersect with what. And what intersect with what, maybe, before I continue. The question about how much an object can be split if there are triangles is kind of hairy, right? Here is a bunch of triangles. Of course, it's extreme maybe, but here's a bunch of triangles in theoretical structure. I'll build n triangles times n triangles, and you see that each one of the blue triangles. Now, if I did not have the painter algorithm in my arsenal, and I need to decide for each sub-sliver of a triangle, is this exposed to you, is this not exposed to you, should I render it red or blue, I now need to take n square, omega of n square decisions, such slivers of triangles, that makes my algorithm very slow. Okay? So if I can avoid it by the painter algorithm, just render one triangle at a time, so nice. Application where I have such general order. Think about the windows on your monitor. Think about the window of your monitor. Assign to them each window this, and let's put our chat for this structure. We decided to assign them so the chat is closer to you than the slides, then done. I just rendered, the monitor first rendered the slide, and then it rendered the chat closer to you. And every pixel in the chat was some pixel change its location. Right? So that's a reminder about the painter algorithm. And the beauty of the painter algorithm is that essentially it says there is, you might have studied, I hope that you studied in 445 or 345, a lexicographical sort, a topological sorting. If you know topological sorting, quick reminder, I have a directed graph with nodes, graph where every edge has a direction, A, B, C, D, E, in this direction. And topological sorting is to give each one a label. For example, 2 will not work actually. So I want another one. So possible order might be 1, 2, 3, 4, 5, 6, 7, where the idea is that I give each node a label, such that if you have an edge from node U to node V, then the label of U should be smaller than the label of node V. That's called topological sorting. I'll give a label to each node. It's unreadable handwriting. Label of V. Label of U must be smaller than the label of V. And if I was able to give such labels to all the nodes, then I called it topological sorter. And it's not entirely obvious to me why the terminology topological here is make its way, but it's a nice word. So that's a topological sorting. And notice that it doesn't have to be unique for this graph, right? I could have switched the rules of 2 and 1, and it still makes sense. Still, I obey this topological sort because every edge, say this one, goes from a smaller label to a higher label. And if I have a set of objects like triangles, and you can do topological sort in the sense of how to sort them, so one is closer to one that is occluding the other, we'll put an edge between them. It, of course, depending on where the viewer is, but if one, with respect to the location of the camera of the viewer, if this one occludes a piece of this one, then I'll put an edge connecting them. Now, it is true that in every directed graph, I can find a topological. Definitely not. Not all. If I want to obey this order, which essentially said you can render them properly, and if one occludes another, then the one occluding one will be rendered after the occluded one will be rendered. That is, this node will have a smaller label than this node because this node is closer to you. The higher you are, the closer to the label. You can also think about it as, when I'm teaching 345, 445, I'm thinking about it as, think about every node as a function task that you have to execute, and this task, D, needs input from this task, A. That is, the input of D depends on what you get from A. And the input of B, and B needs some input from D, implying that I can start executing B only once D is done. So finding a topological order of the nodes is equivalent to find the schedule of all these tasks so that I don't need to stop one of them and says, you cannot proceed until your different task will be executed. This labeling is just a schedule at which each one is rendered. And you see, there is a lot of freedom. Now, it's not necessarily unique. Is it clear that every directed graph always have a topological order? Absolutely not. For the sake of time, A, B, C. The moment that you have a cycle, of course, you cannot find such an order. But if there is such an order between my triangles now where I put an edge, if one occludes the other, then there is an edge between them. To be precise, if any point of this triangle occludes any point of this triangle, which kind of assumes that I don't allow them to cross each other, but if any point of this occludes any point of this, I put an edge between them. And that will determine whether the painter algorithm will work or not. And see how cool it is. And by the way, why am I teaching you all this painter algorithm? Because the painter algorithm by itself is probably not what you can use for realistic data, but you can replace pieces of it that are very useful together with GPU. We have a slide coming. So let's assume that I was able to build the BSP binary space partition, and I don't have any plane any object that crosses a plane, which is actually not the case with O4. You see that O4 is crossed by somebody. But let's assume that I can build the whole tree and nothing is crossed. And now I need to render all these triangles, segments in 2D, and I need to find an order for them. I have access to the BSP of this set of triangles. I have the location of the viewer. And let's say that the location of the viewer is right here. and I approach a root, and it could be that, let's assume that I'm not on L directly, otherwise it's easily modified. I'm not on L directly, so my viewpoint is in one quadrant on one side of L, say below L, or below L, I'm on this part of the tree. And this part of the tree, everything above L, all the objects over here are on the other side. But the idea of the painter algorithm, which I don't know about you, I found the painter algorithm highly counterintuitive when I heard about it first time, because it sounds like you should start rendering from the things that are significant and then see if you need to add more details as you're getting further away. And it's not a bad intuition, but it's definitely the opposite of the painter algorithm. Okay, so I have my BSP. I want to apply the painter algorithm as is. My viewpoint will define approaching the root. I now have two nodes that I will call one the far node, and one is a near node, the one that contains me. And I'm going to first render all the triangles in the far node, because I'm using the painter algorithm. First render everybody in the far away region, and then render all the triangles in the close region. How should you render each such triangle? Recursively. But each node in the tree defines its own half plane and defines its own closer and further. And one thing that convince yourself that there is no object. If my BSP is all legit, then object in the far side cannot occlude objects in the near side. That is, shoot array from the viewer toward an object to the far side, toward object in the, object in the, object in the near side will never be occluded by object in the far side. Kind of obvious, I think. That is, everything in the painter algorithm works perfectly. Because obviously, object in the near side can occlude object in the far, but that's fine. Can I build a BSP for any set of segments in 2D? Well, I need to tell a bit more. Can I build a BSP without having to cross segment? I want that all my cuts, every segment will be either on this side of the cut or this side of the cut. I mean, it's a cute puzzle. It's somehow a bit easier in 3D, by the way. Can I find always a BSP for triangles in 3D? 3 pseudo triangle. Show the class.
Can they intersect?
Good question. Let's assume that they don't intersect. My geometric models are legit. Arrange for me these triangles so I cannot build a BSP for them. Because follow the logic. If you can find the BSP, then the painter algorithm works. There is a clear order. Somebody wants my triangle to show the class? Yeah, so yeah. Okay, now I found it a bit more challenging actually to do it in 2D. If there are segments in 2D, can I always build a BSP for them? The answer is no, not always. There is a case that I cannot find a BSP because the 3 triangles, I cannot use the painter algorithm for them. Why? Because there is no clear order. There is a cycle. So cycles here implying I cannot build a BSP. Right. To have an edge between two triangles, it means that one pixel of this guy, any pixel, occludes one pixel of this guy. I don't care which one. And at the same time, this might occlude a pixel of this, and at the same time, this occludes a pixel of this. So I cannot build a BSP without cutting objects, splitting objects for this input. That's a 3D case.
That's a 3D case. So, all over 2D, can you just draw a triangle out of triangles?
Go ahead. So, 3 segments.
3 segments, yeah. Just make a triangle out of those segments. Without any space, but have the vertexes touch each other.
Let's assume that they don't intersect. It's not highly relevant for this class, but we are almost there, so it's not a cute puzzle.
Yeah, I was thinking, could you then do another one of
So-
those, but like rotated on the outside? No, like around it, like circle.
I mean, kinda, but I mean, I need to prove that no line, I cannot find any line that will be there without cutting any of the objects. Can you see an example with 3 segments?
Draw the letter A.
You draw the letter A.
Where are you going to press?
Should I be obnoxious?
Yeah, go for it. Oh yeah, so that's always the problem.
No, you're almost there.
Yeah.
Perfect.
Yeah.
Okay, not even in 3, in 2D. Nobody agrees? I cannot shoot away here. Okay, so does it mean that, okay. So does it mean that painter algorithm is nice theoretically, will not really work not only because triangle intersect, but in general, you know, you have billions of triangles. If you need to pass through all of them, it's lots of work. Even if you can find a BSP without splitting object. Does it mean that BSP are not useful? It's absolutely wrong. You are still using BSP for a lot of things. Essentially, let's talk about the basic construction I had. Remember the notion of RV, the region of a node V. Just because I didn't explicitly say what it is, RV. So R of the root of the tree, or R of the parent of the root actually will be, R of the root of the tree will be everything, the whole space. When you're going to the left subtree, it's everything that's above L1. Going to the left, then everything that is below L1 and also below L3. So it's this intersection of 2 half spaces or half planes. And in general, if you look at the path to every node of the tree, it's intersection of half planes. Where for each half plane, you said I'm above or below this half plane, to the left or to the right. So what can I do with a BSP? Lots of things. Here is my here is my I. Here is our forced room. Forced room or something like this. And here is our BSP. Let's check. And here is L1. L1, this L, the one that sits at the root of the tree. The one that sits at the root of the tree. L1 is right here. What does it tell me? I'm looking at this direction. There is a part behind me. Everything in this subtree, I don't need to render it. Probably are not that lucky that it happens immediately in the root of the tree, but of course, as you're going down the tree, it means that there is portions that you completely filter out because they don't intersect with the force-room at all. If you don't intersect with the force-room, and you can find, because remember, as you are paving your way from the root down to internal nodes, each node, you remember what is a region that it corresponds to. It's intersection of half-planes. The moment that you realize that an internal node, similar to the way we did a report in a quad tree, you intersect that region is not relevant to what you are going to render. It's in the wrong direction, doesn't have intersection with the force-room. Leave it alone, no reasons to visit all its subtrees. What else? How else can we use it? We can say objects that are in the VFAR, since they're in the VFAR, we can do a lot of other things. Right? We can render them with lower resolutions. They are further away from us. Maybe we can make maybe you can prepare a billboard and store this billboard. So it's this billboard already at the root of a node that you just declare as too far away from me. Said it's not a single billboard, but you're saying it's in the background. I don't need it in so much details, and it means that even if I rendered it once and explicitly I do need to visit all of them, and then I'm in an interactive game and maybe I moved as a player a bit, maybe objects that are in the background shouldn't be updated. They're far away. But they need to be updated. They need much less attention than objects that are near you. How do you know what's near and far? It's by traveling the BSP and see what the camera and with relationship with different half-planes. Again, once you have a half-plane that does not intersect the force-room, leave it alone. OK. Yeah. We already have it. We have it with the Z buffer. Just you can still use the BSP the moment that the scene is too large to be conveniently updated for all the triangles. Let me do something with this font. OK, so which data structures did we have so far? We had BSP in general. We had quad trees as one example of BSP. And now I want to tell you about something that is not a BSP, but is so useful, including in graphics, that definitely worth the time to talk it over. So probably in practice, that's the most common tree. Most useful for databases, geometric databases of any type. Again, it's one data structure that is not optimal to one particular application, but is optimal, but is very efficient for many applications. And think about the case that you want to render to use a tree for rendering, but at the same time, the tree also represents interaction between the players and one player to another, or one player in the environment. So all these applications, R-tree will do very well. So let's tell you what is R-tree. I'll tell you about it in 2D, but it works very well in every dimension. So what is the input to the R-tree? The input is a set S of shapes, segments, triangles, and so on. And I want to build a tree in the following way. I'll pick a pair of all triangles, and I'll decide that I want to cluster them. They are close to each other. They are roughly in the same region. So in the leaf of the tree, I'll put them as siblings of each other, and I'll consider their bounding box. Bounding boxes are always a good idea. You have the min and max in each dimension, x and y, that determines the bounding box. So I decided that I want to cluster 8 and 7 because they are nearby to each other. I cluster 6 and 5, put them as siblings. Similarly, I'll cluster 3 and 4. Similarly, I'll cluster 2 and 1. Now, I decided that 7 and 8 are siblings, so in their common parent, what do I store in the parent? The bounding, or the bounding box of their, that encapsulate both their bounding boxes. That's what I stored in the root of 7 and 8. What will I store at the root of 6 and 5? Root of 6 and 5 will be the bounding box of 6 and 5. Make sense? So storing the box is very easy. Just store the two antipodal corners, lower left, upper right, for example.
The box intersects with 4?
Sorry?
Is it okay that the box intersects
Yeah,
with 4?
I mean, yeah, this tree doesn't need to, tries to have nice properties, but I'm constrained by the data. That's the best I can do. Oh, it's a very good thing to do for this data, but no. It's not a BSP, but it's still very useful. Similarly, I cluster 3 and 4. Similarly, I clustered 2 and 1. And now I'm going to build the next level of the tree. I decided to cluster the box of 7 and 8 and the box of 5 and 6, the yellow boxes. So that's what I'm storing at this root, the bounding box of these two bounding boxes. It's very easy to compute the union of two bounding boxes. Right? You're just looking at the minimum of the two minimum of x, the same for y, same for z. Here, the purple node over here is a bounding box of this bounding box and this bounding box, which in turn includes, of course, each one of the bounding box includes all the objects in its sub-region. Okay, and finally, I have the root of the tree that just contains the bounding box of the whole thing. Is this useful for array shooting? Absolutely. You're shooting array. What's a big rule? If my array doesn't hit a bounding box of a root, then it obviously doesn't hit any bounding box of the children of the root, or the descendants of the root. So it's just a very efficient way to filter out big part of the trees that are not relevant for array shooting, or not relevant for object intersection in general. You want to know what is in your forest room. The moment that you have a bounding box, the higher in the hierarchy, the higher in the hierarchy, the better. The moment that your forest room doesn't intersect one of these bounding boxes, don't bother checking its descendants. We talked about ray shooting, ray tracing among segments in quad tree. It's very similar over here. Just what do I do if I have the changes are completely obvious, right? I have two bounding boxes with the object that they contain, each one with the object that they contain. The more I'm tracing my array, and I just follow my RNC. Maybe as opposed to quad tree, I don't need to exit the first quadrant to enter the second one. So I do have to keep attention to which bounding boxes and what are the relevant pieces of the trees that I need to interpret. So there is not obvious theoretical bound that you can give in such R trees. But I think that the efficiency about how many operations it saves is quite clear for any of the applications that we discussed in this course, right? So that's R tree. There are a few bounds that you can give. What's the height of the R tree? That's easy. In general, if I have n triangles, it will be it's obvious. Log 2 of n, right? That's not much. So if you need to just do point location, here is my finger. I want to do point location. Does it imply that it really takes always log n? Not really, because it could be that bounding boxes overlap with each other. Hopefully not. A lot of the performances depends on what was your initial, sorry. That's not what I wanted to do. A lot of the performances depending on how did you cluster the objects or, to start with. Right? If you have good clustering, well, since I created this figure, it was very easy for me to generate the segments where it's clear what should be segment with what. If the triangles are larger, it may be less obvious. And you'll find, of course, as many theses as PhDs that needed publication about ways to optimize R trees, obviously. But that's a big idea of R trees when you fit all your R trees into the memory. How do I find all the triangles that intersect any query region, like the forestrom? Once again, if the parent is completely disjoint from the forestrom, then don't bother any of the children. If the query point is entirely inside the region, then actually it doesn't help. As long as you are not disjoint from the big bounding box, if you do have any overlaps, then just push this query to both children and let them decide for themselves if they have any intersection or not. Now, the merging schemes that I showed you assume that I take two segments, two triangles, and cluster them. In practice, it makes sense to actually take 3, 4, more like 100 triangles and find their bounding boxes, and then cluster 100 other bounding boxes into one node with 10,000 bounding boxes and so on. Why is this so efficient? More efficient? Because if you're using a disk, probably you don't. If you're using your solid state memory, whichever, you still write to your memory while you are basically what makes your memory slower is moving big chunk of memory. You're moving big chunk of memories, and it's optimized to move what is in disk is just buckets. I mean, if disks are less popular, it doesn't, but you're still moving big chunks of memory. So if you are already writing or reading 4 kilobytes from one piece of the memory to another one, if already the units of reading or writing are 4 kilobytes, then let's compress a lot of data into this 4 kilobytes, a lot of children. Why is this so useful? Because, and I'm using disk here just to highlight something that is very slow versus main memories that are much faster. Why is this so useful? Because what really depending on is the height of the tree. That's a limitation of how many accesses do I need to do to visit slow memory from read memory. What is the height of the tree when I'm doing the search? So I'll much better ask the CPU to work harder, and in return, the height of the tree will be low. Even if it's sub, because the bottleneck usually is a read-write much more than the CPU itself. Great. But again, what you are really paying for are the seek operations that will appear here maybe at some point. Moving along. KD trees. Yeah.
How do you visualize an R tree in the non-binary space, like log base 1,000? How do you split?
Same thing. I just cluster. I'll do some clustering by saying, pick one of your triangles, pick the 1,000 nearby triangle. Sort all the other triangles, look at the 1,000 nearby triangles. That's one cluster. Next, move to the next one. By the way, it's also very efficient in terms of moving objects. But nothing here is limits to 2D. Bounding boxes work in any dimension. And it also works very well if your nodes are moving. You want to track who is near Starbucks because you want to send a voucher for a $50 deduction. You want to move anything that involves movements, and so you need to update the R3 every once in a while. Two more data structures to the list. KD tree, I'll show it 4 points. More theoretical applications, doesn't handle other objects that well, but as usual, many variants of it. What is KD tree? D for the dimension, so in 2D it would be a 2D tree. Names are not very meaningful by all means. So quad trees, we said, the moment that I need to split, I will split at the middle of the x value and the middle of my y value, ignoring the data. KD tree will say something else. KD tree will split by, I look at all the data. This region will be the root of the tree. And then I decide to split my data by a vertical line. Where will I place a vertical line? In quad tree, I place it exactly in the middle. The x made sure that this distance equal to this distance. In KD tree, I'll make sure that the amount of data that I have on my left and my right will be as equal as possible. Right. For points, I can fit it perfectly, plus minus 1 if it's an odd number. If it's triangles, then I'll try to find it so the number of triangles that are fully to the left or fully to the right are roughly the same, or I cut it, meaning triangle. So that was my first cut. That is, I halve the data into the left and right. And now I switch direction. I switch direction. It's important to switch direction. And I look at all the data on my right side and find the y value so that out of all these points, number of points on the left or on the bottom, number of points on the top, should be as equal as possible. And I don't care at all what happens on my left side, only what will happen to my right side. In my right side, I keep moving this horizontal segment downward until the number of above, number of points below is the same. And repeat the same on the left subtree. And now we are back to horizontal. If it was 3D dimension, then we would alternate by parallel to x, y, z, x, y, z, x, y, z, until you are down to individual nodes. Okay, so in the root, I stored L1, the first line that I used. Its children will be L2, having the 2, having the right side, and so on. And once again, it's hierarchical data structure. Once again, every node V has a region RV. It's easier to compute it in quadtree because it's just a rectangle. Right? For every node V, RV is just a rectangle. maybe open to infinity rectangle. Everything about ray tracing is still valid. Everything about finding for a node what are the other nodes that are closest to it are still valid. Height, logarithmic, kind of obvious, log n, and so on. And you can, and at least theoretically, you can say more things. Answering a query region, finding the points inside the region. And let's talk about it for a moment. This reporting, if I want to report what are the nodes inside a query rectangle, but that if I want to report each one of them, if I want to count them, I can say the moment that I have a region, a node of the tree that is fully inside the query region, I just cared about the number of nodes. So I can store some augmented data. The term is augmented data structure. I can store augmented data structure, augmented data, augmented field on each node, telling me how many data points I have underneath each node. But we saw similarly more sophisticated parts like store per every internal node a few images, billboards of looking at the data of this node from different directions, so you can just push it as texture into your Z buffer, and you do, as long as you don't need to render it explicitly. We saw it in the case of quad tree, same for KD trees. Okay. Some bounds, there is a nice bound that tells you in the worst case, you will visit for an axis parallel region, more relevant more for theoretical parts. If you have a node, that's a maximum number of nodes that you'll ever visit per rectangle wedge. But it's a very, very pessimistic upper bound. Usually you are visiting much fewer. Just because usually you are either filtering in, it's inside my region, or filtering out, this node is completely outside my region very fast. Okay. It's kind of fast to build the KD tree. It just involves sorting all the points by x, by y, so it's only n log n. Slides it from algorithm/computational geometry. It's efficient in memory, but space is linear, basically, and so on. And yes, quad trees are also very relevant for queries like Forstorm. Talked about it. Yeah, go through it. Finally, and here is cell decomposition. That's like a really easy data structure. So I defined some size of an edge length. Let's say 1, the half is just a coordinate. I'll decide that I want to split my world into regions of size 1 by 1, or in general, I'll decide about some so I don't have R in the tree here. There are no trees. So I'll just call it R. So R is this length. This is R. And this is R. And for the moment that I did it, I split my world into cells of size R, 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 and so on, into blocks of size R, R, R. And now I want a data structure that will allow me all the standard operation, ray tracing, shooting who is near me to know what are the triangles that are, if I have a few triangles, at which cells they are. And I want to make it efficiently. Of course, a triangle might split a few cells, but you'll probably want to take R so that a triangle will not cross huge number of cells. But otherwise, there are, of course, many variants of this data structure. You can do it hierarchically, for example, but let's start from the simple case. I need a data structure for my set of points, triangles, such that I place my finger right here, and you'll tell me where you place your finger, which is in cell 3.2, in the grid cell 3.2. I didn't write it explicitly. The moment that you decided about R and the moment that you decided about the origin of the axis, you basically divided the whole world into this grid of cells of size R. Here I used R as just one. And now my whole world is divided into exactly infinitely many cells, each one of size R. And I'll assume that each cell knows what are the triangles that stores it. And now I need a data structure such that when a query point, let's give it a name, a query point Q, told you about Q, right here, you'll tell me what are the triangles, or the triangles of the, that are crossing or intersecting the grid cell of Q, or the nearby grid cells. So far it doesn't sound very tricky. Build an array that have an entry for each one of the cells, and for every such entry, every such cell stores exactly the objects, the triangles, that intersect this cell. Okay, option one, build an array that have an entry for each one of the cells. Why is this a bad idea? Because there are infinitely many cells. And I don't want infinitely empty cells. And almost all the cells are completely empty. Almost all the cells are completely empty. What should we do? We are using a hash function. Kind of similar to the ones that you used in you studied about 345, 445, such that you take the point q.x and q.y, and this hash function will refer you to a hash table such that for every cell ij, there will be one entry inside this hash table. Now, as you know, for hashing, maybe there is more than one cell, mapped to the same entry in the table. But if your hash function knows what it's doing, it's likely only 1, 2, 3. Yeah.
What do the entries contain? Triangles?
Yes. Whatever information is stored with the cell. So vertices, triangles, whatever happens inside the cell. But, and what is the size of this hash table? It's usually 2 times n, where n is the number of triangles, or n is the number of items, that non-empty cells. N is just the number of non-empty cells. What should be my hash function? It should be geometric. I want to make sure that as long as I have 2 points that are in the same cell, they'll be hashed in the same way. The result of the hashing function will be the same for 2 points in the same cell. Of course, there could be collisions. There might be another cell that will be hashed to the same location, but that's unavoidable. But what I can definitely make sure, or to make it efficient, I don't want to look in the hash table at any other entries besides the entries that is relevant for my query point. So what should be my hash function? I'll just give you the result for the sake of time. What I'll usually do is take Q of x, divide by R. R, remember, the size of the hash table. That would be my first coordinate. And usually I'll multiply it by some constant, A, plus we'll write it. Let's explain. Because it's really, really efficient data structure. It really was spending a second on it. So I have some expression here that produce an integer, and this integer might be larger than m. M is, as usual when we are talking about hash tables, m is number of cells in the hash table. So I'm going to produce an integer that might be larger or smaller than m. So I'll always do it modulo m. So I'll get a legit index into the hash table. Now, my query point q might have float, non-integer coordinates, might have real coordinates, somewhere inside the cell. I want the 2 points in the same cell will be mapped into the same 2 points in the same grid cell should be mapped into the same entry in the table. What should I do? Remember, R is the edge length, implying that all the points, in this case R equal 1, all the points from x equals 0 until x equal 1 and y between 0 and 1 should be mapped into the cell, and I'll give a name to this cell. This cell will be 0, 0. This cell will be 0, 1, 1, 0, and so on. That's like the name of the cell. Now, P imply if R is different than 1, then all the values of x between 0 to R should be mapped to 0, which is exactly what you're getting by doing the flow. Same point here. All the values for y between 0 and R should be resulted in 0. All the values between r and 2r will be mapped to 1, and so on. Now, from now on, you're just using standard technique of hashing. Take the first number, multiply by your phone number. Take the other value, multiply by your other phone number. This integer should be as strange as possible. And voila. And we are done with this. And that implies that for a query point, in theory, for a query point, I can find, as long as if my cell intersect with only one triangle, then I should find it in a constant time. Essentially, I can find all the triangles with my query point in a constant time, one access to the hash table. Right? And it's pretty slick. And why do I need the hash table? I said it, I'll repeat. Why do I need the hash table? Because without the hash table, I need to store all the cells in the table, including empty ones, or alternatively to store them in some sorted way or balanced way, but then I need a search data structures. Here I enjoy both the simplicity of the hash table. I mean, there is some annoyance of getting used to hashing, but once you did it, then it's absolutely simple data structure and extremely fast query point. Giving the query point, it's constant time to access. Who lives with me in the same cell? And of course, million variants. If you don't like that it's uniform cells, then play quad tree-like. Cells that contains many triangles do something hierarchically. But of course, now you are trading simplicity versus maybe efficiency. Okay, and let's move to modeling. So, so our next topic, for the sake of time, people, all clear? Hash table, R trees, quad trees, painter algorithm. Quad trees, always BSP. KD tree, always BSP. R trees, not really, but very efficient. And don't care what are the type of objects that you are storing. And don't care if objects intersect or not. And if they are moving or not, it's fine. The efficiency might be compromised in R trees, but it's extremely flexible about what it can, what types of input it can eat. Modeling, describing shapes. Wireframe, or no, just describes the wires, don't play about it. Fill it up, making it a geometric shape. You want to be able to design a shape, and one of the applications that I'll show you will actually be about designing a shape where the endpoints are given. Worth mentioning this case, we didn't speak, we don't have much to say about it in this particular course, but don't forget volumetric representation. I give you like pixels, I told you about volume, I told you like how transparent it is to light, or how much water it contains, which would be like the output from an MRI machine. But that will be volumetric representation. Okay, wireframe, kind of obvious. I'm just scamming through the slides. You have access to them, but not much to say beside mentioning it. Volumetric data, you are limited to the size of a voxel, the 3D pixel. You'll find people very serious in geometric processing that will say voxels are all you need for any data structure and don't worry about any other representation. And you'll find other parts. Worth mentioning, constructive solid geometry. Maybe I want to tell my shape as a sequence of Boolean operation between geometric primitives. What would be these Boolean logic operations? The or, the plus, the union of two operations, intersection, subtraction, takes the points which are on A and not in B, or takes the complements with respect to another shape. So why am I telling you about all of it? Because it's a very convenient way for me to generate shapes by such a sequence. If I have an idea of a shape that I want to render, and that's how I want to show it. So how can I create this shape with a hollow part at the middle? I'll start from a cube. I'll take the cylinder. I'll do the union of the cube plus the cylinder, creating the cube with the top of the cylinder. Erase from this part this other cube box, which will create this notch over here. Another cylinder will create the hole in the middle, the axis, and so on. Very convenient to add the input in this part. Will be very tedious. Yeah.
Where do the triangles we've been using, like from the WebGL, fall in? Or which one of these?
So in this case, I would say if I want to generate a model, I can generate the model by such an interface that would be way, way easier than controlling vertices of a triangular mesh. Once I decided that that's a shape that I want to create, and to render it, I will probably have to switch to triangle at some point along the way. Somewhere between, if my GPU likes triangles, and I have a lot of these shapes, and at some point I need to generate the shapes, and to generate the normals to the shape. Right? If I want to control the guard shading or the Phong shading, and that will be more obvious there. But that's, as I mentioned, as an orthogonal part of, if I have an idea of a shape, what is a convenient way to tell the computer that's the shapes that I want? Like the version that probably will not work would be specify moving individual point, one after the other. What else? We want to talk for a moment about implicit versus explicit representation. So if I have a function z, which is z of xy, nothing wrong about it. I can specify it also as a function in the terms f of x, y, and z equals 0. For example, I can speak about all the points in the space such that x squared plus y squared plus z squared minus r squared equals 0. R squared is some constant, and what did I draw? I draw a sphere of radius r. But all the points that satisfies it, x, y, z that satisfies it, are all lies on a sphere. Why is this more convenient than writing it as a function, z equal to this creature? Because function just meets for every x, y, just one value of z. That's one parameter, and as we'll see, that's one reason that we sometimes prefer implicit representation. Here I caught it the same way, both values that are on the top of the sphere and at the bottom of the sphere. It doesn't have to be a unique point for every x and y, which I do have if it's a function. Parametric representation would be when I'll have two other parameters, u and v, or phi and theta, and I'll say every point on the surface depends on phi and on theta. Why would I want to use this representation? because I want to do texture mapping, and presumably the texture is given as an image that I want to wrap on the sphere, like the globe. So using phi and theta will be this representation. And we'll see another reasons to work with parametric representations. Okay, and implicit is just a special case. Okay, now when we'll talk about curves, maybe I'll give you some motivation before that. So remember we talked about, here is a triangular mesh, 1D triangular mesh, and I want to do Phong interpolation. Phong interpolation involves interpolation of normals. And in this interpolation of normals, remind you, we decided that for a vertex V, we will have the approximated normal at V, which would be, for example, the average of the normals of all the triangles that are adjacent to this vertex. So I decide about the normal, approximated normal at V, approximated normal of U. And then I can approximate the normals at all the intermediate points. And why do I need these approximated normals? Well, because I want the whole thing to look smooth. But maybe besides just looking smooth and without changing the number of triangles, you want to assign some curve, and you actually want to control the curvature or the normals of each point on this curve that will go through all the vertices. I'm doing it in 2D. Normally it will be a surface that goes through all the normals, and you'd like to control it, to control this other surface that is going through all the vertices, but you'll still have plenty of degrees of freedom that will make it looking more longer or shorter. So in short, I would prefer to have a parameter t, and t will tell me how long along this curve am I, and t will be a different representation. I want to generate a lot of curves. Like Bezier curve will be one, Hermite curves will be another one, but I give you points, P1, Pn. And I might move these points with the mouse. They might be the vertices of a triangulation. And now I want to automatically generate a curve that will go through all these points and will connect them and will be the surface that I need to generate. And I can move these points and maybe change other parameters that we'll see in a second that will control this curve, maybe. And one application would be to control the normals in this interpolation. That this curve is like the boundary of an object that I want to generate. So if my only problem is generate a curve that goes through all these points, that's not very challenging. Here is one. The user will move the points with a mouse, and I'll connect them by a polygonal line. And that's fine. Besides that, it looks terrible. Right? It will be, if that's a normal that you're generating, it's not smooth in any way. Don't worry. So One option is polygonal line, right? Connect every 2 points by a segment, or connect, or create the triangulated mesh. But it looks terrible. It's not a nice aerodynamic shape. I want something smooth. I have endpoints. I'll be done in 30 seconds. One option, polygonal line. Not very nice. Other option is polynomial of degree n. N is the number of control points. That's the other extreme. You can always find a polynomial that will meet these points exactly of degree n, except that it's a very bad idea. Working with polynomials of high degree is not convenient. What are we willing to suffer? We're willing to suffer polynomial of degree 2 or 3, because 3 is just doing binary search. We can always find if two such polynomials meet or where they meet. And so polynomial of degree 3 is usually the optimum. So how am I planning to do it? I'm planning to create something that will go through the first through the first 3 points, and then I'll create something that will go through the next 3 and the next 3 and the next 3, and somehow I'll create these segments so they stitch nicely to each other. So that is called a spline, and we'll talk about 2 specific types, namely Hermite splines and Bezier splines, that are very friendly to generate, and these are like Lego bricks that I can put together to form points, and in addition to just controlling what are the points that we are going to, that's our last demo from today, I can generate, I can move the point C, B, A, and my curve is guaranteed to go through this point, but in addition, I can decide about where these curves, what the normals, at which direction the curves hit next to each one of the points, and I'm guaranteed that the curves will actually be continuous. I will not have holes moving from one vertex to the other. It will be very graceful movement. It will be continuous, and even the first derivative will be continuous. So it's really very elegant transition from one segment of the spline to the next. So that is waiting for us next meeting. Any question about bureaucracy, final that is approaching? Too early to it. OK, I mean, basic result for the final, some overlapping with the midterm, a bit more material, some overlapping, but definitely not all the material from the beginning of the year, and the format will be exactly the same. Thank you.
Is it going to be roughly the same way?
I think that formally I need to do, it's 2 hours rather than an hour. Not that I care about the time, but yeah, no, it will be a bit more. But same proportion, like the ratio between, what is this,